Okay, so this time let's just start talking about complex differentiation. And in the study, differentiable functions were real variable, right? We took such function defined on intervals. But for complex variables, we have to select domains in an analogous manner, which should be open. So for any open set, pick a point z in U and let f be a function from U to complex. We see that it is complex differentiable at z if the limit exists. So here, the division, h is a complex number, right? So z plus h is a complex number. This is a complex number, so this is a complex number. So this is also a complex number. So we are doing complex division here. And the limit is the limit in C, okay? So this looks the exact same as an R, but is quite different because the division is complex number division. This limit is denoted by f prime z or df dz. It is called the derivative of f at a. Sorry, should be z. It's a typo here. Derivative at z, okay? So if f is differentiable at each point, we say that it is differentiable on u. Sometimes we say that f is holomorphic on u. So we use the word holomorphic is to specify complex differentiability as distinguished from real differentiability. Right? So we're going to use holomorphic. Okay. And notice that if f is holomorphic on u, then the derivative function, right? We have to find a derivative function. If f prime is continuous, then we say that f is continuously differentiable. So if you study multivariable calc, it basically says that f is a C1 function. If f prime is differentiable, then we say it's twice differentiable, and continuing, we state it is like an infinitely differentiable function, right? So we have a proposition that differentiable implies continuous, and the proof is actually the same as in R, right? We want to estimate this limit. Well, this expression is equal to, you divide by h and multiply by h, right? Because h approaches 0, so doesn't matter. We can divide by something that is non-zero, right? And now, as again, the limit of a product is the product of the limits. In the first lecture, right, I think it's limit of functions, right? Somewhere here. Limits of functions, right? The limit product is product of limits. Even everything is complex. So here's a product here. Each limit exists, right? Because this limit exists because f prime is differentiable, and this is equal to 0, so this limit also exists. So we can split the limit, and the limit on the right hand side is equal to 0, which means that this is equal to 0, which means that f is continuous at z. Okay. The summation, derivative of f prime g is f prime plus g prime. And this is also immediate from the theorem that limit of sum is the sum of the limits, right? And the product is also differentiable, and we have the product rule which matches our real case. Complex is the same because we want to estimate this expression. So basically we subtract this quantity and add this quantity back. And now we can factor this, right? This expression is equal to this summation, right? Because we can factor out the z minus g of z plus h factor out, which gives this expression. And from here, we can factor out the fz, right, which gives this. And we just take limit, right? Limit of product is the product of limits. So because g is continuous, so if we take limit h goes to 0, right, this goes to f prime z, and this goes to gz because differentiable implies continuous. Similarly here, which gives the desired result. And the quotient rule also holds, right? If g is not 0, then the quotient is differentiable, and we have the exact same formula as in the real case. And yeah, so we prove the differentiability of the quotient 1 over g. So this quantity is equal to this, right? So if you do some basic math, right, it will work out. And I think there's a typo here. I think that should be like this whole thing over h, right? This whole thing over h. So there's a typo here. 1 over h times this, right? 1 over h times this, right? So this will give, this goes to g, sorry, maybe let me use a different color, right? So this goes to gz plus hgz over gz minus gz plus h, right? And we flip the sign so it gives a negative sign here. Yes, everything is okay, right? Okay. And we take the limit. G is continuous, right? G is continuous, so this gives g prime z, and sorry, G is differentiable, so this gives g prime z, and G is continuous, so this gives 1 over g squared, and we have the negative sign here, right? Okay. And okay, so the general formula is just apply the product rule, right? Apply the product rule and gives the same thing, okay? And we're also gonna walk through the power rule, right? For any integer, right? This holds because, right? And also we have the chain rule. Okay, the chain rule. Suppose f is the open set, right? From u to v, g is from v to c, where u, v are open. These functions, and that f of u is contained in v, right? So that we make sure that, like, right? Then we can form the composite function, right? So that the function will be defined, and we're gonna differentiate it, which is the chain rule, right? Let w equals to fz. Assume f is differentiable at z, g is differentiable at w, which is fz, then the composition is differentiable at z. And we have the chain rule formula. Okay, so the proof again the same as in calculus, right? So first suppose that f is differentiable at z, and we let phi h to be this function. So phi h, so this is a constant, right? And this is a function, so phi h is defined is equal to this. Then we multiply h over there, gives h phi h, and also f prime, we also move this over there, right? So we have, yes, this equality. And also, the limit of phi h as h tends to 0 is 0, because if we just take limit both sides, right? The limit of the difference is the difference of the limits, right? Because this to h, right, is the same, there's a constant, right? And this goes to f prime z, so this whole thing goes to 0, which is this, right? So furthermore, even though like phi is defined like for non-zero h, right, for only sufficiently small h and for h non-zero, we can just set phi 0 to 0. We could just make this definition, and this still remains valid, right? Formula still remains valid, because if h is 0, then fz minus fz gives you 0, and 0 times 0, right? Well, anyways, it's just 0. So this formula still holds. Now, conversely, suppose that we have a phi defined from sufficiently small h and a number a such that this holds, right? So this, if you compare them, you see that they're quite similar. Instead of, we replace fz by a, right? So if we have a function phi such that this holds and also this holds, right? This is formula 1 prime. Then we divide by h on both sides, right? and take a limit as h goes to 0, right? So this means that f prime z is equal to a, right? If you take this as h goes to 0, right, this thing goes like, yeah, right? So f prime will be equal to a. So the existence of such function phi is equivalent to differentiability of f. So we're going to make this observation to prove our chain rule. And the proof is here. So let w equals to fz, and let k be the increment, right, of this. So this quantity will be equal to this quantity, right? G of w plus k, right? This is w plus k, because w plus k is equal to fz plus k is equal to fz plus fz plus h minus fz, right? So it cancels out, it equals to f of z plus h. So this is equal to this, and g of w is g of f of z, right? So because g is differentiable, right? So there exists a psi k, a function psi, such that the limit, right, converges 0 as a k converges 0, and we also have this quantity holds, right? Notice like it is similar, right? This expression here and this expression here, right? So w plus kw, g prime k plus k phi k. If we change from k to h, right, this is the same thing, h, ah, h phi h, right? Right, this is, we just apply the observation above. And this thing, we simplify furthermore with those substitution. It will be g prime of this, right, this is k, plus k, which is this, times psi k. And then we divide both sides by h. Okay. And now we divide both sides by h. So this is equal to this. So we divide both sides by h, gives this thing divided by h, right? Which, like this whole thing divided by h gives you this expression, right? And yeah, as h goes to 0, k goes to 0, right? By the continuity of f, right? Continuity of f as h goes to 0, right? This goes to 0. So k goes to 0. But as k goes to 0, this thing goes to 0, right? So taking h goes to 0, we see that this thing, which is this thing, goes to g prime w of f prime z, which is g prime f of z times f prime z. Right. Okay, so some last notes. Holomorphic function for opposite set to another is called a holomorphic isomorphism if there exists a holomorphic function that's the inverse. Okay, so say a function that's a holomorphic isomorphism, there exists a inverse of it that is also holomorphic, right? Which can be viewed as like the inverse in the category of holomorphic functions, right? Yes. And if the domain is U, then it's called a holomorphic automorphism. Some terminologies. And we're going to come to the Cauchy-Riemann equation. So, as I said before, right? We can write f in terms of real imaginary parts, that each of them is from U to R, right? This is real number and this is real number, I times a real number. And it's reasonable to ask under what condition differentiability means for U and V. So we're going to derive equivalent conditions on UV for f to be holomorphic, which means that we want to evaluate this quality first in two different ways. First, let h goes to 0 through real values, right? So for h not equal to 0 and h real, we get this. We just substitute in, right? because h is real, so it goes with the x, right? Minus f of x plus iy, f of z, right? Z is x plus iy. So this will be simplified to this, the real part and the imaginary part. And we let h goes to 0. This is the partial u partial x. This is partial v partial x, right? Now, if h is purely imaginary, right? I'm sorry, h imaginary. I'm sorry, this is a typo here. Then, oh, never mind. Yes, h is real because we want like ih here, right? So f of z plus ih minus fz over ih, right? We're gonna decompose it like this. And we go back to our u and v. It's gonna be look like this, right? And then this here, I and I cancels, and 1 over I is actually equal to negative I, right? 1 over I is equal to negative I. Why? Because 1 over I and I gives 1, right? And also negative I times I, which is negative 1 times I, which is negative 1 times negative 1, which is equal to 1. So negative I and 1 over I must be the same because the uniqueness of inverse of multiplication in a field. So here, exactly. So f prime z will be equal to negative I of u with partial y and also v with partial y. So if we equate them with the real imaginary parts, we said this and this must be the same, right? Which is ux and vy. And this must be the same, which shows that uy is equal to the negative of v partial x. Okay, so yes. And this is called the Cauchy-Riemann equation. Okay. And now conversely, suppose u and v are a function defined open U with continuous partial derivatives. I mean, it doesn't need to be continuous, but at least partial derivative exists, okay? So furthermore, suppose that u and v satisfy the Cauchy-Riemann equation. We write it like this, then we can show that f is differentiable, okay? So to see this, the proof is kind of technical. So maybe you can take a look at this. It is just by mean value theorem and R, right? So eventually you're going to estimate some quantity like this, right? You're going to show that, okay, you're going to show that this is true. It shows that f is differentiable. And yeah, and that's really it. So we need some notes on the calculus from f that it maps from A to B to C. So yeah, as I stated in my notes, I would like to indicate a few results for functions defined on an interval, but the values are in C rather than R. Okay? So we can just consider the real part and imaginary parts. First of all, we have this important fact that for z is equal to x plus iy, then the maximum norm of xy is less than or equal to the norm of z, which is this, right? So you go this inequality, and this thing is less than or equal to 2 times the maximum of them. So this is a very important chain of inequality that you should be verified by yourself. From here, we shows that f is continuous if only if real and imaginary are continuous. Okay? With the derivative of f, we define it as, again, the same thing, right? And yeah. So from here, we have a proposition that it is differentiable if only if real and imaginary parts are differentiable. And we have the formula that f prime is the real part derivative plus I times the imaginary part derivative. And the proof is wordy, but it's not wordy. I mean, it's just easy enough, right? Let f prime be this. And then we can estimate this quantity. And then just by direct computation, right, we get this. But remember, the real part of this is this thing. I mean, of this is this thing minus u. And the imaginary parts of this is this thing minus v, right? V, u, v are in reals. And because, right, because we have this, right, shows that this limit exists. This limit also exists, right? And the derivative is exactly this plus this, right? Now, conversely, if we have real and imaginary parts and continuous, we again estimate this quantity, right? If we let the real part derivative is equal to u and imaginary part derivative is equal to v, then we want to estimate this quantity. Well, this by definition is equal to the real part squared plus imaginary part squared, right, with a square root. Now again, from here it's less than or equal to 2 of maximum of each, right? Maximum of each. But they can be made arbitrarily small is because we have this and this, right? So we can show that f is differentiable. This goes to 0. So the derivative, it is u plus iv, which is this plus u plus iv. So we're done. And yes, if its derivative is constant for all x and ab, the f is constant because the real part, if the derivative is 0, then the real part and imaginary part are all 0, and the real and imaginary parts are constant by our knowledge from first year calculus, right? We also, we're going to consider the chain rule, right? If f is ab to c and g is from cd to ab, also differentiable, then we have this thing. So we can apply the chain rule from calculus, right? So we know this. But what if f maps into u and h is a holomorphic function, differentiable, holomorphic? The proof is really the same as the proof of the chain rule for two holomorphic functions. It's really the same, if you can check. Right? And here's the proposition of it. We just summarize this as follows. Right? And to discuss the integral calculus for a complex value function, we just define it. We define it as the integral of real part plus integral of imaginary part with I, right? And we also have the fundamental theorem of calculus, right, of this, okay? And lastly, gonna include some angles under holomorphic maps, which is the introduction to the concept of conformal mappings. In this section, right, a single geometric property of holomorphic maps, saying that they preserve angles. We're going to make this precise. So let gamma be a function from AB to U. We just talked about this, right? It has the real and imaginary parts. Assume that gamma is differentiable, so we have this, right? Now let f be UC holomorphic, then we have the chain rule, right? And for this gamma prime t, we can interpret it as a vector in the direction of a tangent vector at the point this. So gamma t is like, if gamma t, right, is gamma at some point, this derivative is like something like this gamma prime t, right? As a tangent vector at the point. Now, if there are two curves that they intersect at some point z0 in the space, so, and like this, right? So first of all, for this one, the direction vector will be this, and for this one, the direction vector will be this. So we have an angle, right? We define the angle between the path at z0 to be the argument of, like, right? Basically the angle between them, right? So maybe if I draw like a better diagram, like this, and like this, yeah, sure. Then at this point, this will be the thing, but here, this point, sorry, maybe this part will be the thing, and this is their angle, right? This is the angle between them. And yeah, this is like the definition, and this is like a clear way to define them, right? So the theorem about holomorphic function is that it preserves angle at each point z0 if the derivative is non-zero. So what it means is that if we have two curves, that meets at an angle, right? That meets at an angle theta something theta, then after apply f, the angle won't change. It might look different. It might look somehow a bit different, right? But the theta won't change. Okay, the theta won't change. So the proof is quite simple, just by chain rule. And the fact that when you multiply complex numbers, you add their angle. Suppose gamma is differentiable curve and f is holomorphic, then we consider sigma as their composition with the chain rule, right? And yeah, it's just application of chain rule directly, okay? And a map with preserved angle is called conformal. So by this theorem, we say that a holomorphic map with non-zero derivative is conformal. Holomorphic maps with inverse holomorphic maps. So we consider about holomorphic isomorphisms. Their derivative should never be equal to 0. Right. Think about this why. Right. So in this terminology, we can say that holomorphic isomorphism is conformal, but the converse is false. If it's conformal, doesn't necessarily to be a holomorphic isomorphism. For instance, if we let U be the entire space deleting the origin, okay, then we define this function, okay? It is everywhere non-zero derivative, right? Is 2z, right? 2z, the derivative is equal to 2z. It's non-zero in U, so f is conformal, right, by the theorem. But it doesn't emit an inverse function because it is not even injective. Okay, so this is some basic introduction of complex differentiation. Just an intro, still an intro. So next time we're going to talk about power series, which will be more rigorous. Okay, so see you guys next time.